Hello, welcome to my channel. This is the first episode on Programming Talks. In this series of talks, I will present to you some very interesting problem to solve. However, don't expect to see those problems in your programming exercises. Actually, I would assume that you are good at it. So the problems selected here will be a little bit more challenging. So let's get into our first problem. Finding all equal pairs in two sorted arrays. So what is an equal pair? Given two sets of data, x from x1 to xm, and the second set y from y1 to yn. An equal pair is an element xi in x and a yi in y, such that xi is equal to yi. So the problem itself is pretty simple. So the programming version would be this. Given two arrays, x and y, each of which contains sorted and distinct integers in ascending order. So x contains integers. They are sorted and they are distinct. Y also contains integer. They are sorted, distinct, and in ascending order. So let's write a C program to find all equal pairs. Here I chose C. You could use any language, of course. So right after you learn the problem, a very immediate thought for beginners would be something like this. Let's assume that array x has m elements, y has n elements. Therefore, for each i, we have an xi. Let's compare xi against every element yj in y. If we happen to find an xi which is equal to yj, then we report a equal pair is found. So for each xi, so I runs from 0 to m minus 1. We're going to compare xi against all elements in y. Here, j runs from 0 to n minus 1. We compare these two. If they are equal, we have found an equal pair. And if they are not equal, then perhaps we don't need to do anything. We just advance to the next j. So keep looping until all j's are tested. We go for the next I. This is probably what a beginners may come out. As we mentioned, if xi and yj are not an equal pair, obviously we don't need to do anything. So the else part is empty. We should compare xi to yj plus 1 in the next step. Now, if xi and yj are equal, then this part may have to do something. If you like, we store the value of I and the value of j so that we know where to find this particular equal pair. And if we also want to count how many, then we have to keep a counter. When we find one, then add 1 to it. After this is found, we compare xi against the next y, that's yj plus 1. So here is something in a programming version. We have two arrays, xx, yy, to store the location of the found xi and xj. This is for I, this is for j. K is a counter, so initially it's going to be 0. So if xi and the yj are equal, we store I into xxk and store j into yyk, increase the value of k by 1. Then we have a break statement here. Why we have a break statement rather than going for the next comparison, that is comparing xi and yj plus 1? Well, when you write a program, try to understand all given conditions. We said both arrays are sorted in ascending order. Their own elements are distinct. Now, if we have found an xi which is equal to a yj, the next element, that is yj plus 1, cannot be equal to xi because all yj's are different. So once we find this yj, we know the next yj plus 1 is going to be larger than yj, which cannot be equal to xi. Therefore, once we have found an equal pair, we simply skip the remaining j, because elements in array y are sorted in ascending order and that the elements are distinct. So this observation is very important. So putting everything together, let's write a function for that. Let me call the function to be equal pair. It takes the input array x with m elements and y with n elements, and also two arrays xx, yy to store their locations. In the function, we have ij and the counter k. So for every I, we compare xi against every element of yj. Once we have found an equal pair, we store the location, increase the counter by 1, and then break out, because all the remaining y's, yj plus 1, yj plus 2, up to ym minus 1 cannot be equal to xi. Therefore, when the outer I loop finishes its work, we have found all equal pairs or no equal pairs. We return the counter value k. So this is our first version. Perhaps a beginner would come up a solution similar to that, except that some of you may still have this break statement missing. Is this solution good? In terms of submitting an exercise programming, this solution works. But is this a really good solution? The answer is no. What if none of the xi is equal to any of those yj? So the inner j loop would loop n times. Each iteration requires one comparison. Therefore, each execution of the j loop requires n comparisons. However, the outer loop I would run from 0 to m iterations. As a result, the total number of comparisons will be m times n, because each iteration for I requires n comparisons in the inner loop. So the complexity or the order of this solution is order m times n. If m is equal to n, it is an n squared solution. I'm sure you may be a little bit skeptical. Is this a really solution that bad? Well, when you look at this simple problem and you get an order n squared solution, it's usually not very good. For beginners, this solution could be an acceptable one. However, it does not use all the given conditions, such as sorted to its maximum. We only used sorted condition to break out. We did not do anything for the sorted array X. If we do not use all the given conditions, our program may not be very efficient. Of course, we could improve this kind of naive solution to some degree, but this improvement could just be minor, which will not affect the overall complexity. When I say complexity, I mean the worst case complexity. So let's take a look at a few simple improvements for the beginners. Let's assume that x0 is less than y0. So in this case, we could find an xp such that xp is larger than this one. But xp minus 1 is smaller than this one. In this case, we know from x0 to xp minus 1, these elements cannot be in the array Y. That is, we find an element xp, which is the first element in X, that is larger than or equal to y0. Because y0 is the smallest in Y, so x0 to xp minus 1 cannot be in Y. In this case, we use p comparisons here to find p. We could remove this part. Once this part is removed, what we need to compare so far is we compare the section from xp to xm minus 1 against the section of y0 to ym minus 1. So how many comparisons we have saved? Of course, p times n, right? Because here we save p iterations, but we use p comparisons to save these p iterations. So we use p to save p times n comparison. So this is our first improvement. If we could cut the first part, we could also cut the second part. Here, we assume that ym minus 1 is larger than xm minus 1. So we could scan down n minus 1, n minus 2, down to ym minus q, so that n minus q is larger than xm minus 1. But the next element, n minus q plus 1, is less than this one. So in other words, we scan down, because we assume this one is larger than this one. We scan down until we find an element which is the first element found, which is larger than this one, but its neighbor is less than this one. And if xm minus 1 happens to be larger than ym minus 1, you just change the array name. So in this way, we know from n minus q to n minus 1 in Y cannot be found in x because they are all larger than x minus 1. In this way, we use Q comparisons to cut y, the length of y, down. So the ranges are reduced to p to n minus 1 and 0 to n minus q. So here is a diagram showing to you this part cancelled, this part cancelled. We only focus on this part. We use P comparison to cancel this part. We use Q comparisons to kill this part. So here, the elements here is P to n minus 1. The elements here is 0 to n minus q. So to compare here, we need n minus q comparisons. But here we have only m minus p elements. So the total number of comparisons would be m minus p times n minus q if we only compare this part. But don't forget, we use P comparisons here, Q comparisons here. So actually the total number of comparison is this. In the worst case, it's still m times n because P and Q could be 0. Therefore, for general use, you may save some number of comparisons. But in terms of the worst case analysis, there is no improvement at all. As we just mentioned, these modifications indeed can speed up the original version. But in general, in doing so, it does not improve the worst case in a big way. Therefore, we have to think differently to break this order of m times n barrier. Think about it before you proceed to the next section. The question is there a better way? Of course, when you see this slide, you know there is a better way. If you have learned sort of data structure, you probably have learned binary search. And if you have reached the data structures course, binary search is a topic must be taught in a data structures course. So why you thought about binary search? Isn't it very natural? Because array Y is sorted. To find an xi in Y, isn't a binary search much faster than the linear search we used? Okay, that is it. Let's say Y is here. Initially, left is 0, right is n minus 1. Every time, as long as left is less than or equal to right, we compute the mid element. That's Y mid. Then we compare the given data against Y mid. If we have found that, return mid. This is binary search. And if data is less than mid, then data is going to be in this section from left to mid minus 1. If it's not, then data would be in this section because it's larger than Y mid. Then the next we search Y mid plus 1 to Y right. So here is it. We compute the location of the middle elements, compare the given data against the middle elements. If it's there, we found return mid the location. Otherwise, which means data is not equal to Y mid, it's either less than to Y mid or larger than Y mid. If that is less than y mid, we search the left portion. That is, we move right to this point. Otherwise, we move left to this position. So that next iteration, we search the right one. And if we could finish the whole while statement, nothing can be found in y. This is binary search. Remember, the array y is sorted in ascending order and all elements are distinct. If you have identical elements that is next to each other, you'll have to do something more, which we won't talk about it here. You may use it as an exercise. So, for binary search, every time we cut the number of elements to be searched by half. Say here, we cut in the middle. Either we search this portion, which is half of the original, or we search this portion, which is also half of the original. So as you know, it takes log 2 of n cuts or iterations to determine whether data is in y or not. The worst complexity is it's not there. It's order of log 2 n. You know this well, I am sure. So we could use this idea to improve our naive solution. It's pretty simple. The outer for loop is the same, the I loop. For I from 0 to I equals n minus 1, we have an xi. And this is binary search. The left initial is 0, the right is n minus 1. As long as left is less than or equal to right, compute mid elements if it's found. Then we record the y value and the location in y. Increase count by 1 and break. I assume you remember the use of this break because the next elements will be different from y mid, which is also larger than y mid. It cannot be equal to xi. So we could skip the loop. Or if it's less than y mid, we search the left part. Otherwise, we search the right part. So the only difference is here. We replace the inner J loop, which uses n comparisons in each iteration. But now, the J loop is replaced by this while statement, which would only loop log 2 n times. In each iteration, we use 2 comparisons, 1 here, 2 here. So at worst, the number of comparisons for each xi is 2 times log 2 of n. But the problem is the outer loop of I is still running for m iterations. Therefore, the total number of comparisons used in this solution would be m, the number of iterations for the I loop, and the number of comparisons in the inner loop. So this is our improved solution by applying binary search. There is an interesting way to think about this solution. We are given 2 arrays. If we use xi to search the sorted array y, then the complexity will be the order of m times log 2n. We could switch the array x and y. Instead of using xi to search y, we could use yj to search x. You just call this function by switching the order to x and y. In this case, the complexity would be n times log 2 of m. this is the array to be searched. Which way is better? You have to determine that. A very intuitive way of thinking about this is we use the shorter array to search the longer array, because we cannot cut down the shorter arrays m or n, but we can use log to cut the longer array. So if n is larger than m, then this one would cut more comparisons. This is an intuitive way of thinking. Then we need a justification. Let's take a look at this table. This is x. This is log 2x. So log 2 of 10 is this. And log of 10 million is 23.253. Rounded up is 24. As you can see, this is the power of the binary search. It's so huge, the difference. So this gives us a more comfortable argument to use the shorter array to search the longer array, because the log 2x would cut the number of comparisons in a more significant way. So we need a proof. This is just an observation. So this is use x to search y. This is to use y to search x. We don't know which way we have, less than, equal, or larger than. Let's do some algebraic manipulation. Let's divide both sides by the product of log m and log n. So this log n is cancelled, and this log m is cancelled. So the left term has log 2m, the right term has log 2n. So basically, we have a function in x. Let's say this function is fx equals to x over log 2 of x. Why we do this transformation? If fx is an increasing function, it means if m is less than n, then fm is less than fn. If m is m over log 2m, less than fn, which is n over log 2n. So we multiply both terms back, we have this. So our conclusion here is, if we could prove function fx is an increasing function, then we should use the shorter array to search the larger array. And here we have a less than sign. So our goal is proving fx is an increasing function. Is it difficult? No. This is the function value of fx. We rewrite this log 2 by taking natural logarithm. So log 2 of x is equal to log x over log 2. So fx is x times log 2 over log x. Now, when you see log x in the denominator, you know there could be some trouble. Because when x equals 1, log 2, 1 is 0. fx is infinity, is here. When x approaches 1, this function goes to infinity. But in that case, it doesn't matter, because the array must have more than one element, right? If you have only one element, one comparison is done. You don't need to do this kind of a comparison at all. So to prove fx being increasing, let's compute its derivative. So df over dx is equal to this one. Now, this is equal to log x squared times log x times dx over dx minus x times d log x over dx. But we know d log x over dx is 1 over x. Therefore, the derivative of f is log 2 times log x minus 1 over log x squared. We are almost there. Let's copy the derivative of x over log x here. Now you know we have the curve like this. To compute this minimum of this curve, we just set df over dx to 0. By setting this equation to 0, it means log x must be equal to 1. When does log x equals to 1? Is this when x equal to e? That's 2.7 something. So we know the minimum occurs at e. So what is the value of fe? We just plug e into here. We have this. Therefore, the point e, 1.88 is the minimum of this function, which means as long as m and n are larger than or equal to 2, using the shorter array to search the longer array is the way to go. Of course, we could still do some improvement, not so very significant. First of all, we could determine whether xi is in the range of y. So as long as xi is greater than or equal to y0 and also less than or equal to yn minus 1, we do search. So that would cut down number of comparisons. But we did not improve the worst case. That's you can never find any xi here. So every iteration, you require 2 log n. For every iteration, 2 times log 2 n comparisons are needed multiplied by m. We could also imitate the improvement we discussed in the first section. We could cut a portion out of x, another portion out of y. In this case, x runs from xp to xm minus 1. When we do binary search, left is 0 initially, and right is m minus q. But that does not improve the worst case, because p and q could be 0. Then, if we know xi is equal to yj, then all elements from yj plus 1 to ym minus 1 are larger than xi. So we simply skip the xi and move on to the next one. This is a very important observation to develop an optimal solution. Let me repeat. If we have found an equal pair, then all the remaining elements are larger than xi. So if we have found an equal pair, we immediately skip to x minus. If we have found an equal pair, we could immediately skip xi to xi plus 1. That is, we could skip the I loop, the outer loop. So the last observation we made can help us to develop an optimal solution. We have every ingredient available from section 1 to section 2 to this section 3. The idea was, as we discussed earlier, if these two are equal, then all elements here are larger than this one. So we skip this one. We immediately take xi plus 1. So simply put, if we have found an equal pair, the next search will be in the range of xi plus 1 to xm minus 1 and j plus 1 to n minus 1. Here's an example. If we have found an equal pair, then the search will be in this section, which means I++ and j++. This is a very important observation. Now, what if xi is less than yj? Of course, if xi is less than yj, xi cannot be in this section. Based on what we explained in the previous slide, we simply try xi plus 1 to see whether xi plus 1 is here. Keep this in mind, xi is less than yj, then the next one in x could be in this section will be xi plus 1. Here is an example. Xi is less than yj. So we try next one, that's xi plus 1. Therefore, as we are comparing xi and yj, if xi is less than yj, we increase I without changing j, because the next xi could be equal to yj. On the other hand, if xi is larger than yj, like this, so yj is less than xi, it could not be in this section. So we try yj plus 1. In other words, if we find out xi is larger than yj, we increase j without increasing x. In summary, we have 3 cases. When we compare xi and yj, if xi is less than yj, so we move x to the next one. Hopefully, we could find it being equal to yj. If xi is greater than yj, so yj couldn't be here, so increase j, so that I hope yj plus 1 is xi. Now, if both are equal, then we move to the next section from I++ to m minus 1 and j++ to m minus 1. In this way, each iteration, we don't know how many iterations yet, but each iteration requires 2 comparisons, one here, one here. If both fails, we reach the third one, so we don't need a third comparison. So let's determine how to start these iterations. Of course, I and j must start with 0. Because every iteration we compare xi and yj. Therefore, we must have xi there. And we must have a j there. So the loop will be I less than m and j less than n. And then we do the comparisons. This is what we come up with. When one exhausts, that is I larger than or equal to m, we have used all elements in x. We simply stop because the next iteration we have no x to compare. Similarly, we do it for j. Now let's put everything together. We still write the program as equal pairs. Set I, j, the 2 indices, to 0, and set k to counter 0. as long as we have elements in X and elements in Y to compare, we loop. If xi is less than j, increase I. Hopefully, we could find xi plus 1 there. Or if xi is larger than yj, we increase j. Hopefully, the next yj plus 1 is this one. And if they are equal, we increase both. Of course, we have to increase counter as well. So this is this simple. Then we have to determine how many comparisons. And this is a bit more complex than the two previous not so good solutions. Look at here. If xi is less than yj, then we use one comparison here. Only one. If we did this and the execution path falls to here, we use two comparisons, whether it's in the then part or in the else part. So each iteration will use maximum 2 iterations and minimum 1 iteration. Of course, I could take m moves, and the j could take n moves. For each move of I, we need 1 comparison. For each j move, we need 2 comparisons. Therefore, the total number of comparisons would be m needed by I and 2n needed by j. This is definitely a worst case because we run out I and j at the same time. If one, say I, runs out fast, then we don't need to compare the remaining y. So is this case possible? Yes. This is possible if xm minus 1, the last elements in x, is equal to ym minus 1, the last elements in y. Then I takes m moves and j takes n moves. So in this case, we need m plus 2n comparisons. Therefore, this is an order m plus 2n solution. So let's say if m is less than m, x is shorter than y. If xi is equal to yi for all I, so we compare x0, y0 equal 2 comparisons. Then we compare x1 with y1, 2 comparisons, and so on. So we need exactly 2 m comparisons. Again, we assume m less than n. If the largest elements in x, or the last one, is less than the first in y, then all comparisons would be increasing I. So I goes from 0, 1, 2, 3, 4 up to m minus 1. In this way, we need m comparisons. On the other hand, if the smallest elements in x is larger than the largest elements in y, then every comparison is a larger one. So in this way, we need 2n comparisons. Because the number of comparisons is m plus 2n for the worst case. Again, we assume m minus n. We could call equal pair with the longer array as x, because comparing x frequently get only less than, and then we increase by 1. And the shorter array for y, hopefully this 2n is less than 2m, and their sum is smaller. So this is our analysis of the algorithm. Let's take a look at an example. This table shows the number of comparison steps in a few adjacent comparisons. And this is the number of larger than we encounter. The previous total and the total currently we have. This is X array, this is a Y array. Initially, I and J both points to 0. And no less than comparisons, and no larger and equal to comparisons. Now, because x0 is less than y0, we move the I, index I++. Then I1 is less than y0. Again, we move I. x2 is less than y0. We move I again. When I goes to 3, x3 is larger than y0. So I stops here. For this larger than, j move to here. In this section, we used 3 less than and 1 greater than or equal to. So we have 3 less than and 1 greater than or equal to multiplied by 2 comparisons. So far, we have 5 comparisons. We have 5 here. We copy the previous one down. Currently, I is at 3. And j was moved from 0 to 1. And this comparison, x3 is larger than y1, so we move j. Again, x3 is larger than y2, we move j again. x3 is larger than y3, we move j again. Now we have x3 less than y4. Here we use 3 greater than and 1 less than here. 3 greater than and 1 less than. So 1 less than use only 1 comparisons. 3 larger than equal to, we need 2 comparisons. So it's 5, the previous one, plus 1 plus 3 times 2. So far, we use 12 comparisons. Now, j is here, and I is moved to 4. Now, I is greater than j. It's here, 14 is greater than 10. We move j. 14, 11, move j again. 14 is larger than 12. We move again. Finally, we reached 14 equals 14. So here we have no less than, we have 4 greater than. So we copy the previous number of total number of comparisons, 12. 12 is here. We use no less than and 4 greater than multiplied by 2. In total, we have 20 comparisons. We copy the diagram here, making all comparisons used explicitly. The shaded comparisons are less than. The remaining are greater than. 1, 2, 3, 4. 4 less than. 1, 2, 3, 4, 5, 6, 7, 8. 8 greater than multiply 2, we have 20. So isn't it the total number of comparisons is m plus 2n. The next step would be I to 5, j to 8. So this shows you the worst case. The last elements in x is equal to last elements in y. Improvement, of course, is easy to avoid unnecessary comparisons. If the smallest in x is larger than the largest in y, or the largest in x is less than smallest in y. The technique used to cut a portion out of the comparison discussed in slides 11 to 15 also applies. But all of these improvements are minimum with respect to worst case complexity. For an example, if we use P comparisons to cut the first section and Q comparisons to cut the last section, so the remaining section in X would be M minus P plus the section N minus Q multiplied by 2 in the Y section. We have to add this P plus Q back. The number of comparisons here is still M plus 2N, meaning you cut the first section of X doesn't make much improvement. Let's have a summary. What did we learn? This equal pair problem is a very good programming problem for beginners. It could be a little bit challenging if you do not use all the given conditions properly and fully. We start with a naive order M times N solution. By the use of binary search, we move on to use the shorter array to search the longer array, which is a M times log 2n solution. And finally, reach an optimal one, M plus 2n. Here are some foods for thought. We insist that the given array are sorted with distinct elements. But what if we remove the distinct condition? For an example, suppose X 3 to 5 contains 4, 4, 4, and Y 7 to 8 has 4 and 4. Then we should report X3, Y7, X3, Y8. And X4, Y7, X4, Y8. Finally, X5, Y7, and X5, Y8. Modify this solution to do the same. Of course, you could use any data structures. But in this series of programming talks, I try to minimize the use of data structures. The next food for thought would be, what if we drop the sorted condition? Well, we still maintain the distinct condition. Of course, you could sort both arrays, and the solution cannot be linear anymore. Why? Please think about it. So that illustrates that how important sorting is. This episode took a programming exercise from this paper. And this ends our first episode. Happy programming. Hope this first episode can help you to do programming a little bit better. And I also hope you will come back for the next episode. Goodbye and good luck.